Hi everyone, welcome back to my channel. So in the last video, we studied MLSTM-FCN and applied it to the HAR data. In this video, we're going to do some experiments, but most importantly, the experiment in which I applied the model without the dimension shuffling. So hopefully in this video, we can learn better about the nature of the data and the LSTM layer of the model to see why dimension shuffling could work in this model, or specifically in this case. Let's study together. Okay, now let's go to our first experiment, and that is applying actually this is MLSTM-FCN without the dimension shuffle. So more concretely, I'm just commenting out the permute layer. So this is the original model, and then in this model, wait, where is it? Generate model, no permute. I'm going to use this function to for my experiment. And basically, I'm just copying the original code, but commenting this one. And to carry out this experiment, I have to recollect the training data and the test data, because earlier our train data has the shape of 9 and then 128. 9, 128, right? But if we don't want to use permutation at all, that means we want to be consistent with the original LSTM and the original API of LSTM and convolution. That means we have to put the input shape as the length of the time series first and then the total variables. So we have to make sure that the shape would be 128 and then 9. So to do that, we copy the code from earlier about stacking the data, but instead of stacking it in the second axis, we stack it in the last axis. We stack it alongside the last axis so that the shape is now like this. Get the number of batch and then the length of TS, the time series, and then the total variable. Okay, the same goes for here. And yeah. Oh, actually, I don't need this. Yeah, just remember. Wait, can I stop this? Oh, yeah. Sorry, I just remembered this. I don't need this. Let's just directly save it. Okay. So now we can see that the input layer is 128 and then 9, which goes directly to the convolution and the LSTM layer directly here. We can see the total parameters is fewer now. Earlier it was 264,000. Wait, where is it? This one. Right? But now that we don't use any permutation, the total parameters is actually lower, which is 245,000 now. Okay, now the training is done. Let's look at the AUCs. Looking from this graph, the AUC seems a little bit better. But yeah, let's look at the accuracies. And yeah, the average accuracy is also a little bit higher, which is 0.914. The earlier average AUC was, yeah, 9. Yeah, it's very small. But I guess the range is smaller by using the original model, 2.1% versus 2.3%. So I guess all in all, there's not much difference in the performance. And even though the best model in this experiment has higher accuracy, which is more than 92.5%, a higher accuracy than the best model from the original model. Yeah, it's perhaps just a coincidence. Let's look at the confusion matrix. You see, the confusion matrix from the best model from this experiment is not looking very good. Well, this is not what I had yesterday. Um, what I had yesterday is more similar. So the confusion matrices were more similar. But yeah. But I guess this particular model, prediction has better accuracy because the errors here are smaller. That's true because we can see the main diagonal has more true predictions there. Comparing to this one on the main diagonal, especially on the sitting and the standing label, we have smaller numbers. But yeah, what I want to say is that even though the dimension shuffling in the LSTM might seem or might feel counterintuitive, it actually works. To understand better why permutation works, we have to look back to LSTM. So LSTM is a recurrent network, right? The neurons are chained, and the output of the first, the output of the output of the first neuron would be the input of the next one. And so what this really means is actually they want to capture, in a sense, the correlation between adjacent values. And now that we permute the data and put it into the LSTM network, that means we want to make this layer captures the patterns between variables, like the pattern of the correlation between between variables for each time point. Because in this case, each time point would be each variable. Okay. And now that we are using the human activity data, it's quite easy to see that if we are standing, for example, we won't have any body acceleration and angular velocity, right? So, yeah, it will show a different correlation pattern than if we do walking upstairs or walking downstairs. So what I mean is that it has a clear pattern because when we stand or sleep, our body has a clear system of that can be captured through the acceleration and the angular velocity. So clear that the correlation, in a sense, again, the correlation or the interconnectedness between these variables can be captured through the LSTM. So that's why it makes sense to permute the data. And I guess because of this, this is also why my project earlier was fail. In my last project, I used the bankruptcy data, US company bankruptcy data, and it has all the companies that are in that data set had the 20 years of history. And then the total variables is 18. They were finance data like gross profit and then current assets and then cost of goods sold, depreciation and amortizations. Those are finance data, and perhaps sometimes it could be like they could show very weak, very weak correlation. So maybe that's why it doesn't really make sense to permute them and to capture the correlation between these variables. But with human activity, it will be very clear when we can see from the communication, the correlation between these variables when we stand or when we walk. I guess that's why, even though we permute this data, we can still achieve a decent accuracy. Okay, now before I move on to the next experiment, I want to mention briefly about the accuracy here. And actually not only the accuracy, but about the setting of how I train the model, okay? Actually this data, HAR dataset, this is mentioned in the original paper, and they can achieve 96.71% of accuracy, so it was a lot higher. But at the same time, they do more advanced training settings, like they applied adaptive learning rate, and then they standardized the data first before going into the model. Those were something that I didn't do in this notebook. And they also put the default values for all the parameters, like the LSTM cells, and then the size of the kernels, and the total kernels for each convolutional stage. Well, we can think of this implementation, my project, as a simplistic one. And the fact that I can still get 90% means that this model can be very useful if we put in the right data. And another interpretation is that we can think of this data as independent. Well, I cannot say independent, but they can be seen as features instead of time steps. Okay, so that's why I have this little experiment. Notice that I had run this before, that's why I am not going to connect this notebook, okay? So this is another modification to the model. We can see that after the input layer and then masking, I use dense layers, followed by a global average pooling. Okay. So, yeah. And then I did the training. Wait. Where is it? This one. This dense layer here. So I put the same total neurons as in the total units in the LSTM layer, so 40 in this case. And since I put in the three-dimensional matrix, the output would be also three-dimensional matrix like this. And then to flat it out, I use the global average pool, which is here. So the final output would be a matrix, or an array of 40 values. And here's the result. This is the average AUC, and then this is the average accuracy, 90.9%. It's not that bad, like, you know, it is worse, it's less than 91%, but the difference is not that much. And it's also quite stable. But of course, it cannot entirely substitute an LSTM layer, because in that layer, in LSTM layer, each cell has gating mechanisms, 4 gates. And these gates are what makes it different, or makes it different from the a neuron in the dense layer. Okay, and then this is the second experiment. So in this experiment, I'm going to use the original model, but instead I'm not going to transpose the data. So the data shape would be 128,9. That means I'm not going to transpose the data before feeding it to the LSTM layer. So it will be consistent with the LSTM part, but it won't be consistent with the convolutional part, because before putting it into the convolutional layer, the generate model function will still transpose the data. So from the point of view of convolution layers, they will think that the length of the time series is 9 and the total variables is 128. And yeah, so this project teaches me to really pay attention to the meaning of each parameter and each layer, because calling a convolution layer to a data set with length of time series 9 and the total variables 128 is actually makes the model really large and perform worse, because it doesn't make sense to capture the shape of a time series of only that has only 9 data points. Okay, the training is done, and we can see that the total parameters in this model by reshaping the data. Actually, the better section title here is experiment where the permutation happens on the convolutional part instead of the LSTM part. When we do the dimension shuffle for the convolutional part, the number of parameters explode 3 times fold in this case, to 733,000. And yeah, the AUC seems pretty much the same. Well, slightly lower, just very slightly lower, but the accuracy drops a lot to 88%. Even though the accuracy range is better, like it's more stable, but the accuracy is a lot less. It's less than 90%. Okay, and well, as the last slide, I'm showing you the references to the data. I already show you the website as well, and the reference to the paper here. Alright, so I guess that's it for today's video. Thank you so much for watching. If you enjoyed this video, please consider subscribing. Don't forget to share and comment and hit the like button. And I'll see you next time. Bye-bye.